It's okay.
It's okay? Yeah.
Oh, but we don't have a chairman.
What's the chair?
Still 3 or 4 minutes to go.
Ah, okay.
Yeah.
We are. Then we wait.
The second speech of the after session is from John from Chile. The title is overview 가지고만 motion cell. Please.
Okay, thank Gambino and Maurice organize this interesting workshop. Okay, so what I'm going to talk about is a work which I have to work with Sudan Mitra, Professor Shiga, and 2 of my students. These 2 diagrams. So first, let me explain what this diagram looks like, and then I can give you a talk, right? So first, since everybody here is doing tangent theory, so this one basically is tangent space of this. If you think they just C hat minus En. En is the endpoint in the Riemann sphere, right? So then this one, you see that it just equals tangent space of C hat minus En plus 1. So En plus 1 is En with 1 more point. Everybody can see that clearly? Yeah. En plus 1 is En plus extra point. So now you see, then the PA is so-called holomorphic projection, speed projection is holomorphic, but it's projection. So then you have a holomorphic map from V. So the V here is a complex Banach manifold here. Complex Banach manifold. Right? So now you have Fn is from V to the Ten is holomorphic map, preserve the base point. Right? V has a base point and then Te has a 0 as base point. Then the question is, can you lift this F to a holomorphic map to the Ten plus 1? Then you keep lifting until you lift into the MC. So this one you can think as a product of the tangent space of this omega I. So then the omega I, union of omega I is actually C minus E. So E actually can be think as union of En, N equals 1, take closure. So E is closer. So then MC is all the Beltrami coefficient, which is L1, but norm less than 1. So now that is so-called lifting picture. So this side picture is called holomorphic lifting. So another side of lifting is called continuous lifting. So in this case, this W is host of a Banach space. It's not holomorphic. Then you have a continuous map here. Then you also said, okay, can you lift it to the Fn, but then until the C. So, but it turns out in the holomorphic motion, this part is hard, but then this part is root 10. So that means as long as you can lift at 1 point, then further use normal sequence argument. You can, but however for this one. So this part is okay, is root 10, but until this part is actually hard. So that's what I'm going to explain to you about these 2 differences. So first, for this part picture, actually, there's another lecture I used to give an overview of holomorphic motion. But today I will concentrate on that's called, this part, this hard part is actually related with something called holomorphic motion. So now this part is called quasi-conformal motion. Quasi-conformal motion. So also I'm going to talk about so-called time quasi-conformal motion today. So okay, so now what I'm trying to concentrate on this part. Then Mitra is going to give a talk, but it turns out I will give his talk. But his talk, why this one is important, because of how we discover something, since what theorem we are trying to prove has to use this part. So a lot of work is joined with Mitra, Shiga, and two of my students. One is Macbeth and Zewa, right? So that's what I want to talk about. So first, let's see what is holomorphic motion. So now we see that suppose V is a connected complex Banach manifold, right? With a base point T0. The E is a subset of a Riemann sphere, C, right? C hat. Then a map from V cross E to C hat is called holomorphic motion. First, that at the base point is identical. Then for T fixed, the map is injected. Then for Z in E fixed, the map is holomorphic. So basically it's like this. So you have many points here, right? So each point is just will move separately. They will not intersect, right? So now in this definition, you can see there's nothing talk about continuity, right? Except on the T part is holomorphic. But it turns out this holomorphic is very strong. This map actually first can be extended to the closure of E, right? So you can maybe extend it to holomorphic motion on the closure of E. So in this talk, I will always assume E is the closed subset. Second, this map is joint continuous. That means it's continuous map from V cross E to C. So then also I can use the Mobius transformation to normalize 3 points, right? So I assume the 0, 1 is in E, and in the 0 and the 1 infinity always fixed, right? So as I said, this actually that's Mania Sullivan lambda show that always can be extended to the closure and also is joint continuous. So that is very useful in a complex dynamical system. However, as I said, in this paper, Beer's 1986, immediately after this concept was introduced, the Beer's and Royden paper immediately realized this one is related with title theory. Basically, it's some kind of fundamental thing in the study of title theory. So first, then, you have this so-called extension problem for holomorphic motion, right? So that means for given holomorphic motion from V cross E, now you think E is closed, right? Can we extend it to the holomorphic motion on Howler Riemann sphere? So because if you can extend, that will be related with measurable Riemann mapping theorem. I think everybody know here, right? So another thing is if that motion is from V cross C hat to C hat, then for every T in V, this map is actually quasi-conformal map. And also quasi-conformal constant can be controlled by this Kobayashi distance from T0 to T. Right, so that's actually a very good one. So if you can extend, so that is basically so this the reason is that's quasi-conformal dilatation of HC is controlled because holomorphic map always contracting the Kobayashi metric, right? Right. So that is because the barotraum coefficient actually is a holomorphic map. Right? So that is actually give you, that's what I just said in this diagram. From here to here is actually time up. As long as you can extend to here, then from here to here is actually just a normal family argument. So then I want to give you a little bit of review, which most of these contains our work, but there are many other people's works. First, for V equals unit disk, this extension theorem proved by Solowkovsky in 1991. The method he used is the so-called discover complex variable method. So, but if you read this, there's a Rojas paper. He really wanted to use solve this kind of problem, use the solve Bertrand equation. So until the 2004, Cherga wrote a paper. Then back to use this generalized Bertrand equation to solve that. So also I had Mitra and Wang interpret this one in the lifting. That's what I just said, the lifting picture to show this. But another thing is for V equals S is an open Riemann surface, right? Not simply connected. Then the answer is yes. If I know if induced monotomy is trivial. So I'm not going to tell you what is induced monotomy. But this one is first monotomy induced by this homomorphic motion given by the Jiang Mitra Shiga paper on 2012. Also in my paper with Mitra and Wang and Shiga has another paper. So now another thing is actually for this thing I think is quite complete. It's like this. So in the Cherga's paper, he actually introduced so-called zero winding number condition. But first he said, okay, holomorphic motion can be expanded if I know if it has a zero winding number condition. But actually that's not right. So basically the right condition is so-called a trivial monotomy condition. So actually we studied many different other conditions. Include the trivial monotomy condition and also so-called guiding isotopic. Then we try to figure out which one is actually if a non-leaf. But eventually we actually get that is zero winding number condition and trivial trace monotomy condition and trivial monotomy condition and guiding isotopic, all the necessary conditions for the extension problem. But however, only trivial monotomy condition is sufficient. But guiding isotopic actually is introduced by in the Gardner and Jean Wang's paper. But that paper proof is actually has problem. But then Jiang Mitra Wang and Jiang Mitra and this all papers fix that guiding. So, but basically, it's monotomy condition is actually sufficient and necessary. All the other basically is not. So that is basically for holomorphic motion. So then for the high dimension one, that's still problems. But however, for V just equals TE, that's a technical space, right? In particular, one number of E contains more than 5 points. Then that is dimension of V is bigger than or equal than 2. Then you cannot understand. That basically is Earth, the 1968 paper show that you don't have a holomorphic section things. So then in my paper and Mitra, we reinterpret that into universal holomorphic motion to show that. But then for other kind of high dimension complex Vanna manifold, right? There's not too many studies on this thing. For example, in the V equals polydisk disk in the CN, I extend that's at least I don't know. Shiga said that he has some idea, but I'm not sure yet. So let's see. So now let's say they come to the quasi-conformal motion. So quasi-conformal motion is defined by Simon Thurston in 1986. This paper is in the same journal as Royden Beers. It's 1986 in ACTA. I mean, that time probably this topic is very hot because both papers published in the same journal. That's very rare. Only talk exactly the same thing. So they actually, okay, in the Beers-Royden paper, they actually try to do the extension problem, but he cannot do the full extension. He said, okay, you can extend it to the disk with radius 1/3 across C hat. But basically, they use so-called Alfred-Wells section. But then Simon Thurston showed that for holomorphic motion, you can find the R, universal constant R. The motion can be extended to the delta R, that's a disk with radius R, cross C hat. So, but since we cannot define the holomorphic motion at that time to how the Riemann sphere, they said, okay, let's change the condition, change to the quasi-conformal motion. So they actually relax this holomorphic condition by this quasi-conformal condition. So that means that now we can take C is connected Hausdorff space with the base point T0. Then E is the subset, also you can think as the closed subset, doesn't matter. Is a subset of the Riemann sphere. A map is called quasi-conformal motion. You first at the base point is still identity. And for each T that's still injected, these two are still like a holomorphic motion. But third, they change this holomorphic condition into the, for every T in the W, any epsilon bigger than 0, there is a neighborhood of T, such that for every A, B, C in the in E, 4 point, the image also 4 point because that's injected, right? So then 4 point you can talk about this cross ratio, right? So here's okay, I will show you what this cross ratio is. So then for different 2 points, you have 4 points. Then cross ratio will be very close. And hyperbolic metric on twice punctual sphere, right? So here's this one is replaced holomorphic condition here by quasi-conformal. Some kind of quasi-conformal.
In this definition, sorry, there is no constant K of quasi-conformality.
No, no, that's the key point. There's now, yeah. So now here is definition. So rho 0, 1 is the so-called hyperbolic metric on the twice punctual sphere, and phi x a b c means the cross ratio of these 4 points. Also, you can normalize it by assume 0, 1 infinity in the E, and 0, 1 infinity is fixed on the motion, right? 0, 1 infinity is fixed on the motion. So now, okay, so another thing is, same thing, you have exactly same questions on the extension problem, right? So here you also have similar like lambda, you can always extend to the bound closure of E. So that means you can take E as a closed subset, that's no problem. You can normalize it. But also the question is, can you, for quasi-conformal motion phi tz from W cross E to C, can one extend it to a quasi-conformal motion on the Howland Riemann sphere, right? W cross C hat. So again, in this case, I think that this notation actually in Mitra's talk, he will say this one is actually first appearing in his thesis. So that's compared to the holomorphic property, then you can control the K, but this is continuous only. So that means you cannot control K, right? So now you see that now that for quasi-conformal motion from W cross C hat to C hat, for each T, again, this one is quasi-conformal homomorphism. That's no problem because the cross ratio is preserved somehow if you can argue a little bit and say, okay, that's quasi homomorphism. But also you given T, then you have a Beltrami coefficient for this quasi-conformal homomorphism, right? But this one is a continuous map. Where continuous map will not contract Kobayashi method, right? So actually that is a big problem later you will see. But okay, so okay, so okay. Anyway, so that is a similar extension problem for the quasi-conformal motion you want to ask. Okay, now here's in the paper by Simon Thurston Simon. So they actually said, okay, if even we cannot extend the holomorphic motion, we actually can extend for quasi-conformal motion. So now they said, okay, for W equals unity interval, the answer to the quasi-conformal motion is yes, right? So now the reason this statement we pay bigger attention on this one because me and Shiga and Mitra wrote a paper, take this result as granted, then we publish a paper in the Israel journal, and then actually is always careful on this kind of thing. So he keep asking us, try to give a proof of this theorem, right? Try to give a proof of theorem. So now I think it is better for us to complete this result to prove this theorem. So I give this one to one of my students. So then the one actually. Then I asked him to try to prove this theorem, right? Because in third paper, Thurston Simon paper, they state that theorem, but basically they do not have a proof. I think the key point that they thought is for if you look at this lifting thing, first step for quasi-conformal motion is trivial, right? It's Newton. But later one, actually they thought it's just like holomorphic motion. It's okay, but actually that main point is for continuous motion, continuous part extension. This part actually is a big problem. So now then I give this problem to one of my students. Then a couple months later, he actually gave me a draft of that. So he may find a common example. Then I sent to the Shiga. I said, okay, we have a common example. Then Shiga said, oh, let's study it carefully, right? Then we actually spent quite a long time to talk about this common example. But then I remember 10 years ago, I gave a talk also in some seminar. Then and Gardner there, they think they don't believe we have this common example. But is very careful. Said okay, but later he was convinced. He actually gave a definition about this time quasi-conformal motion. What I'm going to talk about. So okay, now here's a counterexample we had. Here's a counterexample. So now the counterexample is C data. So they exist a closed subset E in the C hat, which infinite many point, and quasi-conformal motion from 0, 1 infinity cross the E to C, such that phi cannot be extended to a quasi-conformal motion from U cross C hat to C hat for any neighborhood base point 0. But actually, in this theorem, you can replace 0, 1 by any path connect the Hausdorff dimension, Hausdorff space. But still, you can extend to a continuous motion. That means you drop this cross-ratio condition, but that still can be extended. So you still can extend the continuous motion, but you cannot extend the quasi-conformal motion. So that is the counterexample. So now, so this one first, well, it's even hard for me to believe, but now it's very clear. This what's happening now. So basically, it's so-called time probably at a limit point, right? So now we have this theorem. So let me give you the. Let me see what time. So what time I should finish? So what time I started actually? Oh, I forgot.
4, so it is still.
4? We start 4, right? Okay. So now, okay, now let's give you the idea of the proof of this theorem. So this theorem said, okay, so you take infinite many point which is accumulate to the infinity, right? Infinity you think that's a point on the Riemann field. Then but then you think about the ratio is actually go to infinity, that means the point is far away from there, right? So another thing, if you think this infinity that's a point in the Riemann sphere, is you like the point accumulated to a point, but the ratio is decreasing very fast, right? So now you take the x as infinite point to the Riemann sphere, right? You have that. So now for this Riemann sphere, right, you have infinite many punctures, right? You have infinite many punctures. Also, each puncture has a far away distance. So now you just draw the simple closed curve, which is only enclosed R2n, Rn, 2n plus 1, right? You just put all the simple closed curve in the Riemann sphere, right? So now you do the Dan twist, right? That's just the regular thing. You do Dan twist, right? So I have a question on this. So you have a lot of points, right? Every point shows a simple closed curve. Then next 2 points show a simple curve, right? All these simple closed curve will not be joined, right? Will not join, so it's joined with the simply closed curve. So that's called alpha n. So now we do this, right? We do the Dan twist, right? The Dan twist around the annulus. So An is the annulus from R2n to the R2n plus 1, right? Ba is the outside, right? Then you, like the Pa is very big. They do the Dan twist on alpha n many times, such that the hyperbolic length of this image curve, simply closed curve, ratio this original hyperbolic length is going to be infinity, right? You take the Pa is large enough, right? You can have that. So, right? So, well, that's a construction, right? You do that. Okay, so now you, okay, here's a picture. How do you do the Dan twist, right? You twist this one to, right? On call curve, you turn Pn times, right? Then this line will just turn like this, right? So eventually, this alpha becomes very complicated. Simple closed curve with a very long hyperbolic length, right? A very long hyperbolic length in x, right? In x. Right. So now this picture I only did once, right? We did it once. One twist. You keep doing twist, right? Keep doing twist. The co-curve is this. Co-curve is this. The green one is co-curve, right? So just do the twist. So okay, so that's the way you do that one. Now you take E is actually all the circle on the Cn plus infinity, right? That's closed set, right? That's closed set. Then you actually do the motion like this. You do the motion is actually if you look at this function, right? You have phi n here. You look at the phi n here. So you take t equals 1 over n plus 1, that will be identity, right? Then you take t equals 1 over n, that will be equals 2 pi I pn, right? Pn times on circle. Okay, so now you just do one interval by one interval, keep doing that So now you actually take the limit, you actually get motion from 0, 1 cross E to the C. Then you can prove what? You can prove that phi can be extended to the continuous motion, right? You just patch all the gap together for a continuous map, right? That's okay, right? But then all the circle actually separated. Then you take a point, 4 point on the some circle. Then cross ratio will not will be bounded, right? Will be bounded. So that is a quasi-conform motion of E. But you cannot extend it to the quasi-conform motion. Why is that? Because if you extend that, every circle will be connected, right? Then you see that then when you do the motion, you actually not only turn the circle, you turn the neighborhood going, right? Right? You think about it, that's one circle, that's another circle. If you turn this around, turn this around, without this between, you can just turn whatever you want, right? But after you turn connected, then you turn is actually when you do this turn, when you do this, then you want to do this turn, this one actually becomes like this, right? So now you can see that eventually will not be quasi-conform map. Okay? Like if you just look at this rectangle, if you measure big enough, this becomes very strange rectangle that is quasi-conform constant cannot be kicked, right? So that is actually a counterexample. So now we come to this so-called time quasi-conform motion. Actually, this definition is given by because we actually sent a paper by original definition. Said, okay, it's better definition is this one. Actually, that is better definition. So what is this set? Okay, so that set is W be a connected Hausdorff space with the base point T0, a map phi Tz from W cross E to C hat is called a time quasi-conform motion. If first at base point is still identity, right? That's right. For each T in W, the map is injected, also okay, right? But now you have to put a so-called time condition. Basically, that should be on every accumulation point, limited point. So that means for every T in W, there exists a quasi-conformal map W from C hat to C hat, and the neighborhood. On this neighborhood, this quasi-conformal motion looks like a global one bestowed by quasi-conformal map, right? So that means you have a quasi-conformal motion from psi from neighborhood across C hat such that phi S Z equals psi S W Z for all that, right? That's actually really eliminated this very complicated limited point. That means at every limited point you basically have some kind of regularity here. So it turns out this definition is actually equivalent to our original definition. So our original definition is too strict, right? Too strict. So said, okay, let W be a connected Hausdorff space with base point T0, a map phi from W to E cross to C is a time quasi-conformal motion. If anomaly first you have at base point is identity. For every T that map is injected, that's the regular, right? The third is actually for every T there exists neighborhood, and you have a continuous map from neighborhood to the MC, that's all diatromic coefficient, space of diatromic coefficient, such that this phi SZ equals WG S dot Z for all the SZ belongs to neighborhood. So WGT means the unique quasi-conformal mapping whose diatromic coefficient is GT as fixed 3.01 infinity, right? Because that's a measurable Riemann mapping theorem that you have a unique quasi-conformal map which is given transfer coefficient fixed 3 point, right? So okay, now the correct version of the first study is such the statement is should be like this. So now you let W be simply connect the Hausdorff space with a base point T0 and psi from psi from W cross E be a time quasi-component motion. Then there exists a quasi-component motion from W cross C hat to C hat such that capital psi is extended small psi. Okay. So now that means you need to replace the time quasi-component motion to quasi-component motion, right? To make it how the extension problem works, right? So now you see a lot of theorem now. That's actually in Mitra talk when you talk about the theorem. We actually first proved by assume this Sebastián result. Now we can just replace this subject by this time quasi-component motion. Still works. So also if you look at Gardner-Lockridge book, they have a lot of places to apply. You use that result as a subject, then just replace it by that statement. Everything works. Okay. So okay, let me give you outline proof of this one. So okay, main step in the proof is actually just like the first step, right? First step. First step. If you here's I think this. Now you come to this lifting things, right? So actually, you see, for holomorphic, this step is difficult, right? But for this continuous one, actually from here to here is okay, but from here to here you have to prove harder, right? So actually, that theorem, main step in the proof of the theorem is like to prove second step actually. So that's that. Okay. So that's the so-called universal holomorphic motion problem. Universal property for this holomorphic motion. So first, you see the W be simply connect the Hausdorff space with base point T0, and phi from W cross E to C is be a time quasi-component motion. Then there exists a unique base point preserving continuous map F from W to the time space of E such that this motion small phi is actually pulled back of this so-called universal holomorphic motion. So what is the capital psi E? Capital psi E is defined like this. You take your time space is defined by all the mu, which is equivalent relative to the E. Then for given point in the TE, then you can define this capital psi mu equals this one. This one is quasi-component motion with diameter coefficient mu, right? Fix 3 points. Then measurable Riemann magnetic theorem said this one is a holomorphic motion, right? It's a holomorphic motion. Actually, this holomorphic motion is universal. That means all the other holomorphic motion basically is a baby of that. Okay. So now the question is that one also universal quasi-component motion? So our counterexample said this one is not universal quasi-component motion. However, this theorem said this one is actually a universal time quasi-component motion, right? It's a universal time quasi-component motion. That means for every time quasi-component motion, you can find a continuous map such that it's just like a pullback of this universal holomorphic motion, right? So that is the key point. That's actually, if you look at this lifting graph, that's actually second part of this lifting. That is I said for continuous part, this second part is harder. But for holomorphic part, second part is actually we can. Right. So okay, so now key point is just as I said is prove this so-called lifting, right? So now you take En, E1, En is a sequence in the E, right? Such that the closure of union of En equals to E. Then we want to have this whether for this Fn, you can easily define by this actually I think the meter is called Nag's problem, Nag's theorem. That means if you take the Yn as a point in the Cn, which such that coordinates are different, then that one will be diagonal space will be universal cover of this one, right? So now here I assume W is simply connected, right? So then the universal cover thing you can leave, right? So holomorphic motion give you the continuous motion give you the continuous map of capital F, as easy to see. But this small f can be get just use covering this, right? Because you have universal covering, then you have continuous method. W is simply connected, then you can always use, right? So that means that reason is that the first part of this lifting diagram is actually not difficult, but the hard part is the second part. So then, what is time condition really guarantee? Guarantee is like this segment distance from Fn x0. X0 is base point. I used a t before, but okay, doesn't matter. Fn from base point can be controlled by this log k wg x0 x for all the n. That means universal control. So then you have some kind of normal family argument. So then the gx is a continuous method. Okay, so now that's my.
Can I see the last
Last slice?
Yeah.
This one?
So this is the T-En is the terminal space of
T-En is the time space of En. That basically is classical time space of C hat minus En.
and this is the universal cover of the
That's the universal cover of Yn. Yn is the Cn.
minus the diagonal.
The coordinates were all different.
You don't need to normalize.
No, Tn is always normalized. 0 is a base point. Yeah. So then every motion, actually any continuous motion you can get from iPhone, right? You just because you have finite point, you take a finite point as coordinates. Then because every point is injective, so that they cannot have the same coordinates, right? So then this capital F is actually mapped from W to Y. Then you can leave that Y. That's a covering loop, right? But for this lifting diagram, this PA is not a covering, it's just a holomorphic split submersion. It's not a covering, so we cannot just say, okay, we can lift here.
Any other questions? Not? So,